Hi guys, welcome to this video. I have collected about 69 questions on electricity based on the OCR Physics A syllabus from their past papers ranging from June 2016 all the way to 2022. And I will be doing this, the first 35 questions in this particular video and the rest in the second video. So let's start off with the first question. We're given that a resistor is connected across a power supply. Which statement is correct about the conduction electrons? A, they travel at the speed of light between the collisions with ions. Well, that's false because there is going to be some resistance, so they will travel much slower than that. B, they make random collisions with the vibrating electrons. Well, they actually make collisions with the ions rather than the vibrating electrons. Electrons move rather than vibrate as they are free to do so. So B is out. Now, they travel at their mean drift velocity between the collisions. Not quite, because mean drift velocity is the average speed with which the charge carriers travel overall in an electric field. And it's always, for the electrons, it is towards the positive end of the power supply. So D is our answer. Now, question number 2 states that a filament lamp is described as being 120 volts and 60 watts. Okay, so we are given the voltage and the power. And which statement is correct, given that the lamp is working normally? Okay, so A, the charge passing through the filament in 1 second is 2 coulombs. Well, that's 2 coulombs per second, which is essentially 2 amps. And we can figure out what the current is because we know that I is equal to P over V. And that's 60 over 120, and that will give me 0.5 rather than 2. Okay, so that's out. Then for B, we have the lamp transferring 60 joules for each coulomb. Now, 60 joules per coulomb is essentially work done divided by charge. So that is voltage, and voltage is not 60. Okay, it's 120, so that's out too. Then the lamp transfers 120 joules in 2 seconds. Well, let's find out. So that's power is equal to energy divided by time, and we are given 120 over 2. And yes, it gives us 60 watts, so C is our answer. Right, let's move on to our next question. Question number 3. A battery of EMF of 8 volts and internal resistance of 2.5 ohms is connected to an external resistor, and the current in the resistor is 350 milliamps. What is the power dissipated in the external resistor? So let's just draw this circuit out, and we are given internal resistor and an external resistor, and 8 volts, 2.5 ohms, and a current of 0.35 amps, okay, is flowing through. So we need to work out the power, and power dissipated could be given in terms of, well, many different forms, but in this particular case, I'll use I times V because I am not given the resistance value. So I know the current, and all I need to do is work out the voltage, or the terminal voltage, okay? Voltage basically across this resistor, okay? So that can be given by this equation, or rather EMF minus I times R is equal to V, and 8 minus 0.35 times by 2.5 will give me the voltage, and that turns out to be, okay, that is 7.125 volts. And from here, I can work out the power, which is current. Okay, so 0.35 times by 7.125, and that gives me a value of 2.49, which is therefore rounded to 2.5, and B is the answer. Okay, so let's check out the next question. And I have question number 4. The diagram below shows a cell with an internal resistance connected to an external resistor. Which of the following will increase the terminal potential difference? So the EMF of the cell increasing, yes, it will, because EMF is, if there are more volts to begin with, there are more volts across the terminal. So that is true because that's the equation, okay? Increasing the value of the external resistance, yes, it would, because V is proportional to R. Okay, and finally increasing the value of the internal resistance. No, that will not increase the terminal PD, because if you're increasing the internal resistance, you're basically increasing there are more volts lost. Okay, so therefore there's less available to the to the resistor, external resistor. Okay, so that's out. So therefore only 1 and 2 are correct, and B is my answer. Okay. Question number 5 says that the graph of the semiconducting diode is shown below, the IV characteristic, and which statement about the resistance of the diode can be deduced from this characteristic? It says A, it is 0 between 0 volts to 0.7 volts. No, the resistance is quite high, up to 0.7 volts, so A is out. It is constant between 1 volt to 1.5 volts. No, because a diode is a non-ohmic conductor. Okay, so it is not going to be constant. And C, it is 0.4 ohms at 1.2 volts. So let's find out whether that's true. It is highly unlikely, because if you look at the size of current, it is 10 to the power of minus 3, but let's just make sure that whether that's correct or not. So 1.2 volts is roughly about 1.11, so it's gonna be somewhere here. Okay, and for that I have a value of, so that is 2 and 10, so 0.2, so 2.2, 2.468, so 2.8. And so if the current is that, resistance is V over I, which is basically 1.2 over 2.8 times 10 to the minus 3. Okay, that's going to be a fairly huge number actually. And that is going to give me 1.2 over... Alright, so that gives me a value of 430 ohms rather than 0.4 ohms. So C is definitely out. And D, it decreases between 0.7 volts and 1 volts. Yes, it does. That's how the current increases. So D is the safe answer. Alright, so in this question, I am given a 9 volts battery, which is connected to 2 resistors as shown, and the terminals X and Y are connected to another circuit that draws a current of 1 milliamp. And the battery supplies a current of 3 milliamps. So we know therefore, and we are asked to work out what the power supply to the circuit connected between X and Y is. So we know that power is equal to current times voltage, and I'm using this equation as just one of the examples. Perhaps there's more than one way of doing this question. So because between X and Y, well, that external circuit is getting 1 milliamps of current, we would have 2 milliamps available to that fixed resistor, 3000 ohms resistor. So if we could work out what the potential difference across that resistor is, it will be the same across X and Y. Okay, so V across that 3000 ohms resistor is I times R, okay, which is 2 milliamps, okay, 2 milliamps times by 3000, and that is going to give me 6000 millivolts, or just 6 volts, okay. So power is therefore equal to, again, 1 milliamp, okay, so I'm just going to leave it as 1 milliamp because my final answer is just in milliwatts. So that's therefore A, okay, so A is the answer. Question number 7 is asking us, what is the correct definition for the watt, given that watt is the SI unit of power? So we know that power is energy divided by time. So that's basically joules per second, okay? Therefore, a watt is joules per second, okay? So C is the answer, okay, C. Right, let's move on to the next question. Question number 8 says that a student determines the resistance R of a filament lamp by measuring the voltage across it and the current in it. And we are given the value of V and I. And it's asking us to work out the percentage uncertainty in the value of R. So this is really a step-by-step approach. Okay, so you work out the percentage uncertainties in V and I. Okay, that is just 0.2 divided by 5 times by 100. And that's just, well, 4%. Similarly, percentage uncertainty in I is equal to 1 over 40. I don't have to worry about the fact that it's in milliamps because the units are going to, it's a ratio such as 1 milliamp over 40 milliamps, so it cancels out. And that gives me a percentage uncertainty of 2.5%. Okay, so because now we are asked about the percentage uncertainty in R, which is V over I, okay, it's just basically going to add up. So the two percentage uncertainties add up to 6.5%, and therefore C is my answer. For question number 9, an electron gun is used to accelerate electrons from rest through a voltage V, and the electrons emerge with a speed u. Okay, and we are asked to work out the speed at which they emerge if the voltage is halved. Okay, so it's basically become v over 2. So for this question, we need to know an equation that is not quite given to us directly, and that is the work done, which is E times V on an electron, okay, as it is accelerated through a potential difference of V, is just half mv squared, or, well, in this case, half mu squared, okay. So because the charge on an electron is E and m is the mass, they are both fixed, we can say that V, the potential difference, is directly proportional to u squared. In other words, we can say that u is, well, I'm just going to use the word, use proportionality still. Okay, it's proportional to the square root of V. So similarly, with this new voltage, which is now being halved, the new speed, which is what we are calculating. So I'm just going to call that new speed as u dash. Okay, so u dash is similarly directly proportional to the square root of, well, V over 2. Okay, so now if we compare these two, I will end up getting C as my answer, okay, because the new speed, the new emerging velocity with which the electrons are emerging, is going to be the older one, okay, but square rooted, okay, with the 2 at the bottom, okay, because of that. So C will be my answer. For question number 10, we are given 2 resistors in parallel, and we are asked to work out what the ratio between the 2 powers is. And for this, we need the relationship between resistance and power, and there are quite a few of them, but the one that I am particularly interested in is power is equal to V squared over R. And the reason why I'm using this is because V is constant, as this is a parallel circuit. So therefore, power is inversely proportional to R. Okay, so what we have is power dissipated in resistor R is just 1 over R, and the power dissipated in resistor of resistance 2R is just going to be 1 over 2R, and therefore that gives me an answer of 2 to 1 or just 2. Okay, so D is the answer. Now, question number 11 is very similar to the one that we just did on, I think it was the second question, so feel free to pause the video and have a go, and come back whenever you're ready. Okay, so let's check what your answer was. So in terms of the potential difference being 12 and the power being 6, we are asked about what is the correct statement. And the first one is just asking, well, just saying that the charge passing is 2 coulombs per second, which is basically 2 amps, okay, of current. For part B, we have, well, okay, so for part A, right, just to be clear, that's definitely not the case, because the current is 6 divided by 12. Okay, so that's just going to be 0.5 again. So for part B, the resistor transfers 6 joules per coulomb, which is just 6 joules per coulomb, as in that's the voltage, and voltage is 12 rather than 6. Finally, C, well, not finally, semi-finally C, the resistor transfers 12 joules in 2 seconds, which is 12 divided by 2, as in the power, because it's energy divided by time, which is 6 watts. So C is the answer yet again. For question number 12, it's asking, which row is correct if the batteries have an EMF of 5 volts and 3 volts? And just bear in mind that the polarity is switched, okay? So this battery is passing current in this direction, whereas the other one is passing through this direction, okay? So basically, there is a net voltage of the net EMF is 2 volts, okay? So the direction of the conventional current is anti-clockwise, though. That doesn't change, okay? So D, it's always from positive to negative, okay? So either C or D is an option. And from there, now it's asking what is the magnitude of the current. So the magnitude, because they are, this is a series circuit, it's going to be the same at X and Y, okay? The magnitude does not change. So D is the answer. Okay, so for question number 13, the diagram shows the conventional currents entering and leaving a junction in an electric circuit, and which statement is always true? Well, we know that the current in is equal to current out, the sum of it. Okay, so the two arrows in are I1 and I3, and the two arrows out, which are I2 and I4. So if you just bring everything onto one side, that basically makes I1 plus I3 minus I2 minus I4 is equal to 0. Okay, and therefore B is my answer. For question number 14, it says a copper wire is connected across a cell. The conduction electrons within the copper wire move. Which statement is correct about these electrons? A, they drift towards the negative end of the cell. Well, no, they don't. They drift towards the positive. So A is out. Okay. They have random speeds because collisions with other electrons, they don't collide with electrons, they collide with ions. So B is out. C, they travel with the speed of light. We know that that's not right. Therefore, D is the answer, as the electrons, the conduction electrons, do collide with the ions, as I said in part B. For question number 15, it says we have a resistor R, an ammeter and a switch are connected in a series to a battery. And the switch S is open, the voltmeter reading is 9 volts. Right, that's the EMF therefore. 9 volts. Right, and the ammeter reading is 0, of course, because the switch is open. Now, when it's closed, the voltmeter reading is 6 volts, and the ammeter reading is 2 amps. Okay, so basically, it's asking us what the internal resistance is. Okay, so we know a good old formula, which is EMF equals V plus IR, and so EMF minus V over I is equal to R. And we've got everything. We've got 9 volts minus 6 volts over 2 amps, and therefore that gives me 3 over 2, or simply A as the answer. For question number 16, we are given a 14 volts DC supply, which is used to charge a 12 volts car battery of internal resistance 0.8 ohms for 6 hours. Okay, and we are given that the current in the circuit is 2.5 amps. How much energy, electrical energy, is provided by the charging supply? So for this one, we first of all, so for electrical energy, we know E is equal to, or work done is equal to V times Q. Okay, so we know that volts, the voltage supplied is 14 volts, and we just need to work out what Q is. So Q is equal to I times T, okay, current times time, which is 2.5 amps for 6 hours, which is 6 hours times by 3,600, because we want to convert it into seconds, and that gives me a value of, okay, 54,000 coulombs. So now all I have to do is multiply 14 by that number, and that shall give me 14 times 54,000, 7,56000, okay, joules, which is essentially D, okay, if you round it to 2 significant figures. Question number 17 says we've got a diagram to show the motion of positive and negative particles in a conducting solution. Which statement is correct? Now bear in mind the conducting solution will have ions, okay, positive ions and negative ions. So the current in the solution is 0. Well, no, it's not, because the flow of charges causes a current. B, the conventional current is to the left, okay? Well, yes, that is true, okay? The conventional current is from positive towards the negative end, so B is the answer. As C and D are definitely not, you know, it says the positive particles are always protons. Well, no, they could be positive ions, such as copper ions, and for D, it says the negative particles could be electrons. Well, always electrons. No, that's not right either, because, again, negative ions could be any ions such as chloride ions or sulfate ions, etc. So that's question number 17 done. Let's move on to 18, where we are given that 1 million electrons travel between 2 points in a circuit. The total energy gained by electrons is 1.6 times 10 to the minus 10 joules. What is the potential difference between the 2 points? So we know that potential difference, or V, is equal to W over Q. And we are given the work done, which is 1.6 times 10 to the power of minus 10 joules over the charge. Now, because we are given 1 million electrons, the charge can be quantified as N times E. okay, or a number of particles, number of electrons, which is 1,000,000, okay, and that's just 10 to the power of 6, and the charge on electron is 1.6 times 10 to the power of minus 19 coulombs. So if I put that in my calculator, let's see what I end up coming up with. Alright, okay, so I end up getting C as my answer. Okay, that's pretty straightforward. Cool, let's move on to the next question. Question number 19 is a real quick one. Which one is not a unit of energy? And that's just D, okay, because D is watts, which is the unit of power. Question number 20. We've got a circuit and we are given that the battery has negligible internal resistance, okay, and the temperature of the NTC thermistor is decreased. All right, well, we know that if the temperature, so the resistance and temperature graph is something like this. So we know that if the temperature is low, then the resistance is high. Okay, so which of the following statements is or are correct? A, well, number 1, current at X increases. No, it doesn't. That's out. The current at Y remains the same. Well, because it is parallel, it would not change. Okay, so that is true. And number 3, the potential difference across the thermistor increases. Well, yes, it does, because resistance increases, and so does voltage. So the answer is B. For question number 21, it says two resistors of resistances 120 and 500 ohms are connected in parallel, and the percentage uncertainty in the value of the resistance of each resistor is 10%. What is the value of the total resistance and the percentage uncertainty? So you could either follow the formula 1 over R equals 1 over, oops, that is, okay, that should work now. So 1 over R equals 1 over 120 plus 1 over 500, which ends up giving me a value of, okay, that gives me 96.77, or, well, 97 ohms, okay, so either A or B is correct, and because the percentage uncertainty does not change when two fractions are added, the overall resistance still has the value or uncertainty of 10%, so A will be my answer. For question number 22, we are given a potential divider circuit with a light-dependent resistor. Again, a very similar question like for the thermistor. So we know, again, for the graph of a LDR, the resistance decreases with light intensity. So it would look something like this again. And it's asking us which row describes, correctly describes the observed change on the ammeter and the voltmeter readings if the intensity of the light is reduced. So if the intensity of the light is reduced, then resistance is higher. Resistance is higher, voltage across the LDR is also higher. So when it says, well, the overall voltage, or rather the voltage on the voltmeter here, would therefore decrease. Okay, it will not increase, it would decrease. So it's either A or D. Okay, and for the ammeter, well, the current, which is V equals IR, okay, or I is equal to V over R, the current would decrease, okay, because if the light intensity is increased, the resistance goes up, and because I is inversely proportional to R, the answer will be therefore A. Question number 23 says, two filament lamps X and Y are connected in parallel, and the power dissipated through X is 24 watts. Okay, that's fine. So, and that across Y is 6 watts. And the supply has an EMF of 12 volts and negligible internal resistance. So what is the total current drawn from the supply by the lamps? So the current drawn by lamp X can be just power, or rather I can just use 24 over the voltage, which is 12, and that's just going to give me 2 amps. And remember, in parallel, the voltage remains the same, so across the bulb Y, it will be 6 divided by 12, which is 0.5 amps, so the total is D. Question number 24 gives us a diagram which has 4 resistances, and it's asking us what is the total resistance between point X and Y. So the two 20 ohm resistors are connected in series with one another, so the total of those two will be 40. Okay, so that will give me 40. Oops, keeps doing that. Okay, so 40 ohms. And similarly, these two 30 ohms resistors are also connected in series, so that will give me 60 ohms. Okay, and now we have a parallel connection. So we can work it out using R as R1, R1 times R2 over R1 plus R2. This avoids me flipping the fraction. So I have 2,400 over 100, which basically gives me A as the answer. Question number 25 says a wire P has length L, diameter D, and resistance of 1 ohms. Another wire Q made from the same material or same metal has length 3L and diameter 2D. What is the resistance of wire Q? So given the fact that you are it's same metal, okay, the resistivity will be the same. Okay, so the resistance formula relating resistivity and things like length and area is R equals rho L over A. Okay, so that's the resistivity. So if I could figure out what the resistivity is in terms of L and diameter, because resistance is given to me, I can work, therefore, the resistance of Q out. Okay, so RP, which is the resistance of P, is equal to its resistivity, okay, times by the length, which is L, over the area, which is pi d squared, okay, pi d squared over 4, sorry. So that will be like so. Now, if I just rearrange it, because I know what RP is, I can just say that the resistance is 1, so resistivity is going to be 1 times pi d squared over 4L, okay, because pi and 4 are constants, I can just remove them and say that resistivity is proportional to d squared over L, okay. So now similarly for RQ, which is what they're asking us, RQ is equal to resistivity times by the length, which is now 3 times as much, so 3L, over the diameter, which is 2D, okay, so that's just going to be pi over, well, pi times 2D squared over 4, okay, and basically, again, if I just now introduce the resistivity in the formula and remove the pi over 4, okay, just because, again, they're proportional, okay, I can just say that d squared over L, which is the resistivity, is times by 3L over, again, pi and 4 I'm ignoring because, as I said, proportional, and 2d squared is just 4d squared, and the d squares cancel out, L cancels out, it gives me basically 3/4. Okay, so 0.75, or A is my answer. In question 26, we are given two filament lamps X and Y, which are connected in series with a 16 volts power supply, and the supply has a negligible internal resistance, and lamp X has a power of 2 watts, and Y has a power of 6 watts, and we need to work out the potential difference between or across lamp X. So we know we are given power and voltage, so I am gonna say that the ratio of powers is, well, basically 1 to 3, okay, and I know power is equal to current times voltage, or power is proportional to voltage because current is constant in a series circuit. So that means that the power across, or rather the voltage across X, okay, so that will be a quarter of the total voltage, which is 16, okay, and that would be just 4 volts, all right, and therefore B is my answer. For question number 27, we are given two resistors of resistances 2 and 4 ohms connected in series, and EMF is 1.4 volts with internal resistance of 1 ohms. What is the potential difference across 2 ohms resistor? Okay, not too bad. So for this question, I am to work out voltage, okay, and I know V is equal to I times R, okay, so I know the R, I just need to work out I, okay, and I is going to be the same because this is a series circuit, so I can work out the total current by doing the total voltage of 1.4 volts divided by the total resistance. Now the total resistance includes the internal resistance as well, and they're all connected in series, so it's going to give me 7 ohms. Okay, and that will therefore give me 0.2 amps of current, for which the voltage will now become 0.2 times by 2, i.e. 0.4 volts. Okay, so A is going to be my answer. Question number 28 is yet another percentage uncertainty question. So again, feel free to pause the video and give it a go. Now, welcome back if you did try it. Let's find out what the answer is. Now, the percentage uncertainty for P is based on the percentage uncertainty in I and R. Okay, so let's work those two values out first. Okay, so I am given a value of 0.2 over 4 times by 100, and that will give me 5%. Okay, and the percentage in R, the uncertainty, is 0.3 over 3 times by 100, which is 10%. So if you said A is the answer, then unfortunately that's not right. Okay, why? Because I is squared. Okay, therefore the percentage uncertainty in P is twice the percentage uncertainty in I. Okay, because it's squared, you times that. If it was cubed, you would times it by 3, okay, and so on and so forth. So 2 times 5, okay, plus the 10. So that will give me B as the answer. For question number 29, the intensity of the light incident on a light-dependent resistor is increased. And we know resistance decreases, as the graph, again, looks something like this. Now, which statement gives the correct reason for this behavior? A, the cross-sectional area of LDR decreases. No, it doesn't. It's independent. B, the mean drift velocity of the charge carrier decreases. It doesn't. Okay, because resistance, well, that just doesn't quite make sense, because if the resistance is decreasing, the current is increasing, and therefore the mean drift velocity will also increase. Okay, so C, the number density of the charge carriers increases. Well, yes, C is the answer. As the magnitude of the charge on the charge carrier increases, the magnitude doesn't. Okay, the magnitude remains the same. So C is our safe answer. Now, we're almost there. With question number 30, we are given that the total energy gained by 20 electrons traveling through a potential difference V is 30 kilo eV. Okay, what is the potential difference V? Okay, so we know that work done is equal to Q times V, and V is therefore work done over Q. Work done is 30,000 eV, okay, which is basically electron volts, okay, and the charge is N times E, okay, so N times E, which is 20 times by E, which is the charge on electrons again. So if you notice, the E's cancel out. I don't even have to use their values because, well, they cancel each other out. So voltage is essentially 30,000 divided by 20, which gives me 1500. So C is my answer. For question number 31, the current at a point in a circuit is given to us as 10 milliamps. Expressed to the nearest power of 10, how many electrons pass through a point in 10 seconds? So it's asking us the number of electrons in 10 seconds. And we are given the charge. Sorry, we are given the current. Okay, so we know Q is equal to I times T. Oops. I times T. So 10 milliamps, which is 10 times 10 to the power of minus 3, times by 10 seconds, okay, is the current, times the time, which is the charge, and then that is equal to N times E. So NE. Okay, so therefore, if we are working out the number of electrons, all we have to do is divide this bit with the value of the charge. Okay, so that is going to be 10 to the power of minus 1 over 1.6 times 10 to the minus 19. Okay, and that will give me a number, quite a big number. Okay, 6.25 times 10 to the power of 17. And so that can roughly be rounded to 10 to the power of 18, and therefore C is my answer. Question number 32 is asking about which electrical quantity has an SI unit amps a second, and that is simply, current times time, and that is the charge, so A will be my answer. For 33, we are given 3 resistors connected like so, and we need to figure out what the total resistance is. So these 2 resistors are connected in parallel, so their resistance can be worked out by using the formula 10 times 10 over 10 plus 10, which gives me, 5 ohms. And that connection is now in series with this 20 ohms resistor. So my answer will be 25, and therefore C is the correct option. Question number 34 has 3 identical resistors X, Y, and Z, and the power dissipated through Z is 24 watts. What is the power dissipated through resistor Y? So we know that this is a parallel connection right here. So power is equal to V squared over R, or because V is constant, power is inversely proportional to R. Okay, so that means that if we have 24 watts in Z, we're going to have, 12 watts in X and Y altogether. Okay, and then if you further half it, it will be A, okay, because they're all identical resistors. Now, for our final question of this video, we are asked to get the best estimate for the elementary charge, E, in terms of both accuracy and precision. So if we look at A, okay, and take away 0.5, we end up getting 1, and then if we add 0.5, we end up getting 2. Okay, so that's that. For B, it is, again, if we take away 0.4, we get 1.1 and 1.9. Okay, for C, we end up getting 1.5 to 1.9, and for D, we get 1.6 to 1.2. Okay, now obviously all are to the times 10 to the power of minus 19 coulombs. Okay, and the value of the charge to 1 decimal place is 1.6 times 10 to the power of minus 19. Okay, so now in terms of both accuracy and precision, so accuracy is how close a given set of measurements are to the true value, which is 1.6 times 10 to the minus 19, and precision is how close the measurements are to each other. Our best option is going to be C, okay, because C is, it has a small range, okay, of values, and it is the closest to our answer. Okay, so C will be my answer to question number 35. So for the rest of the questions, I will be doing another video. Okay, so do check it out, and hopefully this has helped you. Try and practice these questions again. I will keep a link ready down below for you guys to have a go at these questions on your own. And thank you ever so much for watching.